Welcome to Comparative Anatomy of Vertebrates. Today, we are diving into a fascinating topic, vertebra classification by Centrum. Imagine trying to build a tall, flexible tower. The shape of the blocks you use will determine if the tower stands, bends, or collapses. In the animal kingdom, the backbone faces this exact same engineering challenge. Let us explore how nature solves it. Now that we have introduced the topic, let us define what the centrum actually is. Why does this specific part of the bone matter so much? The centrum is the massive, solid central body of a vertebra. During embryonic development, it forms around or completely replaces the notochord. It acts as the primary weight-bearing structure of the entire vertebral column. Furthermore, it provides crucial anchor points for the neural arches, which protect the delicate spinal cord. Biologists classify vertebrae into 5 major categories based entirely on the geometric shape of the front and back faces of this centrum. Understanding what the centrum is leads us to ask why it evolved into different shapes. The answer lies in evolutionary biomechanics. When early vertebrates transitioned from buoyant water to terrestrial land, their backbones faced a new, relentless enemy: gravity. The spine had to stop acting merely as a stiff rod for swimming and start acting as a complex suspension bridge. If a leaping frog had flat, stiff vertebrae, its spine would snap. Conversely, a heavy elephant needs rigid, compressive strength to hold up its massive weight. The shape of the centrum perfectly dictates an animal's locomotion. With this biomechanical challenge in mind, let us look at the first 2 types of centra. First, we have acolous vertebrae, which are flat on both ends. This shape is typical in mammals. It provides excellent compressive strength to support heavy body weights, but it offers very limited flexibility. Second, we have amphicolous vertebrae, which are concave or hollowed out on both ends. This is the standard shape for most fishes and some amphibians. The hollow spaces between these vertebrae are filled with remnants of the flexible notochord, allowing for limited, smooth motion in all directions through the water. Moving beyond flat and concave shapes, we find centra designed for much greater movement. Procolous vertebrae are concave on the front end and convex on the back end. They fit together exactly like a ball and socket joint. This allows extensive movement without stretching the spinal cord, which is perfect for the twisting motions of modern reptiles and frogs. Opistocolous vertebrae are the exact reverse, convex in front and concave in back. They serve a very similar ball and socket function and are commonly found in most salamanders, as well as in the incredibly long, sweeping necks of some dinosaurs. This brings us to the most complex shape of all, the heterocoelous centrum. Unlike the simple curves we just saw, heterocoelous vertebrae have complex saddle-shaped ends. These saddle shapes interlock perfectly with one another. Why is this necessary? It allows for extreme vertical and horizontal flexibility while completely preventing dangerous twisting motions that could sever the spinal cord. This brilliant evolutionary engineering is exactly why birds, like owls, can turn their heads almost completely backwards to groom their feathers or spot predators, all without causing any damage to their internal anatomy. Before we move on to the mathematics, let us visualize these 5 shapes side by side. On the screen, you see the lateral cross-sections of adjacent vertebrae. On the far left, the acoelous joints show flat vertical faces pressing together. Next, the amphicoelous joints show 2 biconcave shapes. In the middle, the procoolus and opisthecoolus joints clearly demonstrate the curved ball and socket mechanism, with one side receiving the other. Finally, on the far right, the heterocoolus joints display their complex interlocking saddle shapes. Notice how the contact area between the bones changes drastically depending on the geometry. Now that we understand the shapes visually, let us look at the physics of why they matter. When an animal bends its spine, massive forces are transmitted across the joints. We model this using the mechanical stress formula, where sigma equals F divided by A sub C. Sigma represents the mechanical stress on the bone tissue. F is the compressive or bending force applied by muscles or gravity. A sub C is the actual surface area of the centrum faces that remain in physical contact. If the contact area decreases during a bend, the stress will spike dangerously high, potentially fracturing the bone. Let us see this formula in action with a concrete example. We are given a mammal with flat acoelous vertebrae, experiencing a bending force of 500 newtons. When the mammal bends sharply, the flat edges hinge open and the contact area drops to just 0.001 square meters. We are asked to find the stress. We choose our stress formula because it relates force and area. Substituting the values, we divide 500 by 0.001. The final answer is 500,000 pascals. This immense pressure is concentrated entirely on the sharp edges of the bone. Now, let us compare that mammal to a reptile with ball and socket procoolus vertebrae. We are given the exact same bending force of 500 newtons. However, because the ball and socket joint rotates smoothly, it maintains its full contact area of 0.005 square meters. We apply the same stress formula, dividing 500 by 0.005. The final answer is 100,000 pascals. Physically, this means the reptile experiences 5 times less stress than the mammal during the exact same sharp bend, safely distributing the force over a wider surface. So we have seen the massive difference in stress. Let us prove mathematically why this happens by deriving the stress ratio. We are setting out to compare the stress of the mammal to the reptile algebraically. We write the stress equation for both animals. By dividing the mammal stress by the reptile stress, the constant force F cancels out completely. We are left with the inverse ratio of their contact areas. This mathematical reasoning proves that stress is inversely proportional to contact area. The intuition here is simple. As the joint hinges open and area shrinks, the stress multiplies exponentially. This understanding of joint stress naturally leads us to consider flexibility. How far can a spine safely bend? We use a simple linear model to find the total range of motion. The formula is theta sub m equals n minus 1 times theta sub j. Theta sub m is the maximum total rotation angle of the entire neck. The variable n represents the total number of cervical vertebrae. Finally, theta sub j is the maximum safe rotation allowed per individual joint. If you increase the number of vertebrae or increase the flexibility of each joint, the total overall rotation increases proportionally. Let us apply this new formula to a real-world example. Suppose an owl needs to turn its head 180 degrees to spot a predator. We are given that the owl has 14 cervical vertebrae, and each heterocoelous joint safely allows 15 degrees of rotation. We are asked to find the maximum possible rotation. We substitute 14 for n and 15 degrees for theta sub j. Subtracting 1 gives us 13 active joints. Multiplying 13 by 15 gives a final answer of 195 degrees. Physically, this proves the owl can easily achieve the required rotation. Now that we have used this formula, let us understand where it comes from. We're setting out to derive the range of motion formula from basic anatomical principles. Consider a neck modeled as a series of n solid vertebrae connected in a chain. The rotation does not happen inside the solid bone. It happens exclusively at the connections between them. The first vertebra connects to the skull, and the last connects to the thorax. Therefore, if you count the spaces between n blocks, you will always find exactly n-1 intervertebral joints. This is the foundation of our model. Continuing our derivation, we can now finalize the mathematical result. We have established that there are n-1 active joints. Each of these joints contributes a maximum safe angle of theta sub j. To find the total rotation, we must sum the angles of all individual joints. Mathematically, this is the addition of theta sub j repeated n-1 times. Repeated addition is simply multiplication. Therefore, the total maximum angle, theta sub m, is exactly equal to n-1 multiplied by theta sub j. This proves how small joint movements compound into extraordinary overall flexibility. Having explored both the anatomy and the mathematics, let us summarize our key takeaways. First, the shape of the vertebral centrum is a perfect example of form following function, dictating an animal's biomechanical capabilities. Second, ball and socket and saddle-shaped centra maintain large contact areas during movement, which mathematically prevents dangerous spikes in mechanical stress. Finally, overall spinal flexibility is the compounded result of many small, safe joint rotations. You have now mastered the biomechanics of vertebra classification. By understanding these principles, you can look at a single bone and deduce how an animal lived, moved, and survived.